So first I'm going to tell you what a function is, then I'll explain it. So I'll give you the words first. It's a relation where every x value that does not look clear. That looks better. A relation where every x value has its own unique y value. It's a relation where every x value has its own unique y value. So you know those games you see in arcades, or sometimes they're in the front of restaurants that has the claw, right? And the claw comes down, you're supposed to grab the animal, right? Which I never ever win, ever. But you put in your $2, and sometimes you get a prize, sometimes you don't. And then if you get a prize, sometimes you like it, sometimes you don't. So it's a little bit of a crapshoot, right? That's part of a game. Well, imagine if drink machines were like that. So imagine you put in your money to get your Diet Coke or whatever, and sometimes you get it and sometimes you don't. And sometimes you get the one you wanted and sometimes you don't. How would that work? Anyone ever done that? Put in their money and then they didn't give you the drink but kept the money? Yeah, right, so you get angry. So everything in math is a relation, but there's a special kind of relation we call a function. And that's really what we're going to focus on over the next 2.5 years, are these functions, because they're the most important. Because sometimes relations are crapshoots. You put in your money, sometimes you get, sometimes you don't. But we like to look at specifically the things that are always going to be predictable. So you put in your $1.75, you get out what you pick, the Diet Coke. You put in a bunch of ingredients and you mix them in a bowl and you put it in the oven and you get out a cake. Imagine if you put the same ingredients and sometimes you got out a pizza. Right? That would be really, really weird. A function is a relation, so everything is a relation, but a function is a special relationship where every x value has its own unique y value. So you put in an x value, you get out this same y value every time. You don't put in an x value and get out different y values, because that's just confusing and unpredictable. So what this means in terms of relationships, grabbing my red pen, is that there's no repeating x values. This is the drink machine, not the claw machine. The drink machine where you put in your money, you want what you want every single time, you don't want surprises. We're going to come back to this idea later in the unit, and I'm going to tell you how to look at a relationship and know if it's a function or not. That's coming back. Let's go to examples of what I mean by this. So let's look at a graph. I don't want to do this in red. And I'm going to go with the most basic graph, which is linear. And so what this means is I can pick any x value on this graph. Let's say I pick that point right there, y there. I don't know, just look good. And I can go up to the graph, and wherever the graph hits, I'm going to get the exact same y value. I'm not going to sometimes get that y value. I'm not going to get two different y values. I'm always going to get that y value. Well, at the same time, let's do a non-example so you can compare one to the other. I'm going to do a graph over here. And this graph is going to be a circle. Which circles are fun. Circles are relationships. They're just not functions. If I pick an x value, and again, why that one? I don't know, it was in the middle. What happens is it hits the graph here, and we get a particular y value at the bottom, but it also hits the graph up here, and we get a second y value. So what that means is that particular x value has how many y coordinates? 2. So this is the drink machine. You put in money, you get your Diet Coke. This is the claw machine. You put out money, maybe you get a little toy, maybe you get a big toy. You have no idea. It could be either. Maybe you don't even get a toy. And again, later in the unit, we're going to look more specifically at how do you tell whether it's a function or relationship. We're just getting the idea right now. Function means every x value has its own unique y value. It doesn't have 2 like this one. What are other ways to express relationships? So graph was one. Formulas, yes. I heard mumble mumble. Equations, which is formula, same thing. So we got graphs, we got equations. Table of values, coordinates. Let's do coordinates. And again, this is just an example, so I'm randomly making up these values. 1 and 2, I don't know, 5 and 7, 3 and -7. And we talked these curly brackets, which are called braces. Sometimes they're there, sometimes they're not. I just want you to see them so you don't freak out later. That's a function. Let's go over here and look at the same thing as a non-example. So here is a relationship expressed as a coordinate pair or ordered pairs you saw yesterday that is not a function. 1 and 2, 1 and 7, 1 and -7. That is not a function. Why not? Because the same value of x, 1, 1, and 1, has completely different y values. So what this means is you can't have repeating x values. That's why it's not a function. The minute the x repeats, it tells you it's got different y values. Again, this we put in 1, we're going to get out 2. There's no other combination there with a 1. Here, if we put in a 1, we might get a 2, or we might get a 7, or we might get -7. And that's fine. It's still a relation. It's just not what we call a function. Function is when each one has their own independent y value. Let's look at a table of values, and I'm going to do horizontal just for lack of space. So a function, 2 goes to 4. I'll do a really obvious pattern this time. 6 goes to 12. 9 goes to 18. 20 goes to 40. Okay. Each of those x values has one unique y value. Let's look at a non-example, so not a function. 2 goes to 4. 2 goes to 12. 9 goes to 18. 9 goes to 40. Why is that not a function? So the same x value has different y values. So if we'll go back to the definition, does every x value have its own unique y value? No. Are there repeating x values? Yes. Function, not a function. We're going to come back to this. We're just giving you the global idea right now. We're going to come back and later I'll show you exactly how do you know whether it's a function or not. 2 definitions you're going to need to know, and again, we're going to come back to them in the unit, is what's called domain and range. Here's the definition of domain. It's all possible x values of a function. All possible x values of a function. Let's see who the smarty pantses are. What do you think range is? All possible y values of a function. If you continue on in pre-cal, you're going to hear the words domain and range a bajillion times between now and graduation. We're going to be focused on domain and range because they're really, really important to functions. Functions are important to relations. Relations are patterns. Patterns is mathematics. So you're going to hear these words over and over and over. What's going to happen is you're going to forget which one is x and which one is y. Who are my left brains? This is how my left brain remembers. I go alphabetically. What comes first, x or y? X. What comes first, domain and range? Domain. So alphabetically, domain comes first and x comes first. Alphabetically, range comes second, y comes second. So if that made sense to you, this is how my brain looks at it. Now, right brains, if you've got a way, I'd love to know it because my brain doesn't work that way. So in a couple of days, I'm going to ask you how you remember which is x and which is y, and then I want you to tell me. Again, we're going to come back to this idea later, but generally what it is, for example, if we were to look at this table of values, the domain for this function is 2, 6, 9, and 20. because that's all the possible x values on the table. The range is 4, 12, 18, and 40. The domain of this function is 1, 5, and 3. The range is 2, 7, and -7. So what we're really doing is just splitting the independent and dependent variable, and I'll tell you why later that's so important. All we're doing today is just these definitions and getting used to what they mean. How are we feeling so far? Good. Second thing we're going to look at is what's called functional notation, which seems so fancy schmancy. Functional notation. An example, if you earn $10 an hour at a job, what's minimum wage right now, by the way? Ooh, you guys are so well paid. In my day, it was $5. So if you earn $10 an hour at a job, there's a relationship between the hours worked and the money earned. They are joined by a pattern. The more hours you work, guess what? The more money you earn. That's a relationship between the two. So we could express this as a relationship, and this would happen to be a linear relationship. So this is something you looked at last year. If you forgot, it's no big deal. But we could say the money earned, I picked M because money starts with M, is 10 times H. What do you think H represents? Hours, right? So I could have chosen X and Y. It's just with this situation, we like to use variables that represent the quantities. So I could represent that as an equation. I could represent it as a graph, a table of values, a coordinate points, a diagram. I just chose an equation. So I could say M equals 10 times H. So for example, if you work 4 hours, how much money did you earn? $40. If you work 6 hours, you earned 60. If you worked 10 hours, you worked 100. So that's actually from last year when you started to look at linear equations. So M would be the money earned. And H would be hours worked. So you don't necessarily know yet, because that's coming up later in the unit, but this is actually a function. It's not just a relationship, it's a function. Because imagine you worked today 5 hours and you got $70, and tomorrow you work 5 hours and I paid you $30. Would you like the amount of money you earn to just be a crapshoot, or would you like a set amount that you earn every single time? So that's when we get into that X values having a unique Y value. You don't want the claw that you work and sometimes you get paid and sometimes you don't. You want the drink machine that you work a certain amount, you get paid a certain amount. And again, we'll come back to this idea. To write this as a function, and at first this is going to seem really, really weird. By the time you hit grade 12, you will have seen this a bajillion times and it's going to be really familiar. We write M, open bracket, little h, close bracket, equals 10H. What the heck is that? What did I add between the equation above and the equation now? The H. Ooh, left brains understand that when smudgy, and that really bothers me. I'll live with it. That's not a multiplication. I'm not saying multiply M times H, and this is what's going to confuse your brains for a little while, because suddenly now we're saying, no, brackets doesn't mean multiplication. That is called functional notation. What happens later on when you get to know more and more functions is we tend to call them all y, and we tend to call the other variable x. And what happens is you get y equals whatever this equation, and y equals this equation, and y equals this, and we start to get confused, and we go, whoa, everything's equal to y. I need a way to distinguish between them. So we might call the first one a of x, and we might call the second one b of x, and we might call the third one c of x, because what it's doing, it's distinguishing between them. Why do we use x? Because that's the independent variable. So this is not multiplication, it's notation. It's called functional notation, and what it means is M is a function. M is a function of the independent variable h. M is a function of the independent variable h. It's not multiplication, and I know at the beginning that's going to seem weird because we've told you now for years multiplication brackets. No, this is called functional notation. The reason we use it is because later on when you get to know a bunch of functions is I don't have time to stop and decide is this a function or not. So if I see functional notation, it's telling me it's a function and I'm good to go. And I'll tell you why later you need to know if something's a function or not. But it's the way of the question telling you this is a function. So remember yesterday when we looked at ways to express an equation and I said to you don't worry about this yet? This was functional notation. So instead of using y equals 3x plus 2, they've told you f of x. It's telling you this is a function and the independent variable is x. That's all it is. It's just notation. The most common letter we use is f because function starts with f and mathematicians are not creative people. If we've already used f, do you want to guess what the second letter we use is? So what comes after f in the alphabet? G, we tend to use that next. And if we've used F and we use G, guess what we use after that? H. And then, no, we don't use I, and I'll tell you why later. But typically, F is the most common letter you see. This is just a variable. This F can be an A, a B, a C. It doesn't matter. It just means it's a function. The independent variable is X. How are we feeling so far? Okay, all we're going to do is take these definitions. So what is a function? What is domain and range? What is this functional notation? And let's look at a real-life example. This is a very applied approach. So if you go into applied next year and you hate word problems, you're going to die. Because applied is all about word problems. It's all about, I saw that F-bomb back there. It is all about applying math to real-life situations. Oh, well, thank you. So if you are not into word problems, applied is not going to be for you. If you are left-brained and you like methods and you like step 1 you do this and step 2 you do that, that is pre-cal. That's what we're doing is setting you up with methods. Applied is you figure out the method because each question is completely different from all the other questions. So we are going to take the same material in Unit 5 and do it applied, and then we're going to turn around and take the same material Unit 6 and do a pre-cal. So you're going to get a really good flavor of what is applied, what is pre-cal. Again, if you don't like word problems, save yourself the trouble. Applied is not going to be for you. Okay. The other thing about applied is they're not cute little one-sentence word problems like pre-cal. They're like this, where there's words all over the place and lots of stuff going on. This is where the read to read becomes really important. You're just going to read it to get a sense. You're not going to panic. You're not going to start to think. Read that first sentence and read the table. What's this about? Bus tickets. What do we need to know? The number of tickets. They've defined the variable. They've told you that they're using N and what it's costing, and they've told you that it's C. So there's times you get to make up the variables, the time they're going to be nice and tell you, and then we're just going to use C and N. Here's all the things we're going to do. We're going to explain why this is a function. We're going to describe the independent and dependent variables. We're going to talk about what is the domain and range. We're going to write it in functional notation, and then we're going to do a bunch of mathy stuff. How are you feeling so far? On an easy scale, this is a 3. Okay, so I know there's lots of words. I know a lot of this stuff is really new. Once you see a couple examples, this is about a 3. So, functions. And I'm going to be a total dork because mathematicians love this. Functions start with fun. Come on, that's kind of funny. You should have seen the look Morgan just gave me. First she drops an F-bomb, then she totally gave me the stare down when I said functions start with fun. How many ways are there to express a relation? 5. What has this question chosen to express it as? Table of values. They could have given you a diagram, they could have given you an equation, they could have given you a graph. They've chosen to give you a table. Why is this relationship a function? So let's go back. What is the definition of a function? Each x value has its own y value, or there's no repeating x values. This is drink machine. You put in money, you get out the pop you want. So what you're doing to answer this is you're looking, does every x value have its own cost? Imagine you rode the bus and today it was $1.75 and tomorrow it was $3, but the day after is 50 cents. Would you enjoy that? No, we're humans. We like constant things. We like to know. We don't want just a crapshoot, whatever you feel like. So is this a function? Does every one of the x values have its own unique independent cost? Is there any of the tickets that have the exact same cost? No. So why is this a function? It is a function. because each number of tickets has its own unique, fill in the last word, cost. So I'm not just saying in general X and Y, I'm saying specific for this situation. For this situation, the number of tickets has its own unique cost. There's no willy-nilly going on here. Describe the independent and dependent variables. In the table, the independent is always first, the dependent is always second. Independent is what you control, dependent is what is dependent on the other variable. What do you control, the number of tickets you buy or the cost? So do you go into Shoppers and say, I'd like 10 tickets or I'd like to pay $20? What do you get to control? How many tickets you buy. So the independent is the number of tickets. It's always the first line or column or row in the table. It's the first bubble in the diagram. It's the bottom of a graph. That's always the independent. Because you asked for however many tickets, what is the lady at Shoppers going to say to you? You pay me, right? So the dependent is cost. What depends on the number of tickets? The cost. See, we're adding in these new words, domain and range. Again, if you continue in pre-cal, you're going to hear them a bajillion times. All it means is the domain is the X values or the independent variable. The range is the Y values or the dependent variable. So domain is X, which is independent. Because this is just a table, we're just going to list them out. What are the possible numbers? It's 1, 2, 3, 4, or 5. What are the possible range values or Y values? $1.75, $3.50, $5.25, $7, $8.75. How much does it cost to take the bus right now for a student? $2.10. It's up to $2.10. Which I think we're the lowest in Canada. In fact, I'm pretty sure we're the lowest in Canada. And what does it go down to for tickets? For 10? For 5. Gotcha. This domain and range thing, we're going to come back. We're just giving you what the idea is right now. So if you're kind of like, that's okay. You just need to know dependent is the range, independent is the domain. And we're just listing them out. Write as functional notation. So we know the cost depends on the number of tickets sold. Cost depends on the number of tickets sold. What's the price per ticket? $1.75. So that would be the normal, everyday, just plain old relation equation. That's just a plain old equation. We want to give this specifically in functional notation. Functional notation says the cost is a function of n, which is the independent variable. This is the functional notation piece. It's not multiplication. It's not c times n. It's just notation saying this is a function and the independent variable is n. Again, later on, we don't want to have to decide if it's a function, so this tells us when it's got that notation, we know it's a function already. Now let's do some mathy stuff. Remember, mathematicians hate words, right? We hate words, they scare us. So back in grade 9, the question would have said, find the cost if you buy 100 tickets. And then you would have gone to your equation and you would have put what for n? 100, and then you would have done the math. That was grade 9. Welcome to Pre-Cal Applied. Now that says the exact same thing without using words. We don't need words. We don't need any of that. That notation is saying the n value is 100. Find the cost. So what is this saying? What is the cost? For 100 tickets. What if I gave you C and then in brackets 7? What would that mean? What's the cost for 7 tickets? What if I gave you C and then inside the brackets I put 12? Find the cost for 12 tickets. All we've done is take away the words. And it's actually funny because functional notation has been around forever. We added the words when we brought language into it. And then in grade 9 we're like, oh no, let's do language because that's easier. Let's not introduce this because it makes people cry. Okay? That's all it is. It's just a short way to write that out without having to write it out. F is actually calculate. So what is C100? Well, it says go to the equation, take out n, and put in 100. So it's not new math. You did it last year. We just didn't use the notation. But this is just substitution and then simplification. What is 100 times $1.75? $175. Who buys 100 bus tickets? It's odd. Took a field trip. There was a Da Vinci exhibit about 3 years ago, and I took 84 students. So I actually had to go and buy 84 bus tickets, and then we all stood outside the school, and when that bus came around like the curve, the bus driver's face just dropped. And we all filed on. There was 4 chaperones, so that was 88 people got onto the bus. It was quite funny. People started getting off. What does CN equals 5,000 mean? So this is different than E. E, we put a number in the brackets. Here we're equating this to something. What they've told you is the cost is $5,000. What do they want you to find? The amount of tickets. This means how many tickets can we buy for $5,000? A lot. Let's hope it's a lot. Again, this isn't new math. We gave you this question last year. We're just taking away the words this year, and now we're asking you with notation. That's all we're doing. The math is not new. Nothing is new. It's just introducing a notation. So how do we solve it? Well, all I'm going to do is take my expression for Cn and put it in here. We know that Cn is equal to 175 times n. That's a grade 7 equation. How do I get rid of the 175? Right now I'm multiplying because it's a coefficient. Opposite of multiplying is dividing. Absolutely. With something like this, yes, for sure. $2,857, confirm. We would need some units because it's a word problem. Tickets. Hopefully that would last a really, really long time. There's everything that we've talked about today all in one question together. Show me your thumb. Getting it, kind of getting, not getting it. Good. If you're still like on the why, that's okay. That's going to come later on in the unit. We're just practicing with the definitions. Number 2. I am not a wordy person, so applied literally makes my brain hurt because I look at this, I'm like, that is so many words. Why? Why do they have to use so many words? Just read to read. Don't overthink it. Just read it. And when you read to read, your brain probably did this. The equation blah blah represents the volume of liters in gas blah blah. Anybody just skip right over that equation? Yeah, and that's okay in read to read. That's why we do it in 2 steps, because if you just read and you're trying to figure out, your brain's skipping half the stuff. What's it about when you read to read? What did you get out of what I just said? The equation blah blah represents the volume in liters of gas remaining blah blah. It's about gas. That's all you need to know going in. You now have a context, which means you're starting to picture it, which means you're slowing your brain down. So now let's go in. What's going to be important? Obviously, this equation. What does it represent? Well, volume of liters of gas remaining in the tank. Do I care if it's a car, a boat, a truck? Not really. And the other variable they've defined is d kilometers. So they've given you a relation and they've given you the two variables. How many ways are there to express a relationship? 5. Which way did they pick? Equation. They could have given you a table. They could have given you a diagram. They just chose to give you equation. What I like to do, because I'm left-brained and we're kind of neurotic like this, is I like to just define them right here so that I don't have to pick through the equation later. So what does V represent? Volume. And I like to put the units so I don't have to search for it later. What's the units associated to this volume? Liters. What's D? Distance. And what's the units? Kilometer. If you don't like that or you don't need that, don't feel you have to do that. That's just how my brain works, is so it's all in that nice little area and I don't have to read later. A, what do we need to do? We need to write it in functional notation. Part B, what do we need to do? Describe why it's a function. Part C. Part D. Okay, determine whatever this means and describe what it represents. Part E, we're going to determine D, when this thing we'll talk about in a second. Describe what it represents. Okay, so nothing new from the last question. We're just giving it a different context, different kind of relation. Example number 2, part A. All we want to do is take that relationship and we are going to re-describe it as a functional notation. All that means is that on the left-hand side, after the variable, what do I put? A set of brackets, and then I fill it in with whatever the variable is on the other side. What's the variable on the right? D. I'm just going to circle for later. That is functional notation. That's all it is. It's not multiplication. It's just notation saying, hey, this is a function. Hey, the independent variable is D. Why is this a function? Well, let's talk about the situation now. What is this relationship describing? The volume in the car's tank and the distance you drive. The more you drive, what happens to the volume in the tank? It goes down, right? That's why it's a relationship. There's a relationship between the drive and the goes down. Why is it a function? See, you're both saying the exact same thing. Say it together. Yes. So for every distance you drive, do you want it to be a crapshoot how much gas you use? Do you want to sometimes use none and sometimes use the whole tank? No, we'd like to know and be able to predict. So it means that for every distance you drive, it has its own unique, more specific to the situation, for every distance you drive, it has its own unique. So it's distance and what's the other variable? So look up where I wrote it above the equation because it tells you right there, distance and. So it means every distance has its own unique volume. Write that down however that makes sense to you. Imagine if every time you got in a car, you had no idea if you had enough gas to go where you were going. That's why we like functions in the math world. We want to know, do we have enough gas to go where we're going? I should have asked last time, does everyone understand my notation IND and DEP? Independent and dependent. Okay, so we talked about with the table, the independent is always the first column or the first row. With the diagram, it's always the first. What with an equation? How do we know which is which? Well, it goes back to here. It goes back to our functional notation. Which one is always in brackets? The independent. This guy is always the independent. Which one is out front outside those brackets? The dependent. Because that's what functional notation does. It identifies the independent variable. So what is independent? The distance. And the dependent? The volume, right, amount of gas. You can also think about it, like I said before, is what do you control, what do you not control? Because you drive, does there become less gas? Or because your tank suddenly changes, do you get to drive more? Which one makes more sense? Which do you control? The amount you drive. D, determine V600. Well, let's actually do first, what does this represent? Because it helps you understand a little bit better. What does this mean? Well, this, without using the words, is saying to you, find the volume when you have driven 600 kilometers. Find the volume when you have driven 600 kilometers. Write that down however that makes sense to your brain. That's the what does this represent. How do we do it? It's direct substitution just like last year. We're going to the equation, we're keeping the numbers, and this is telling you take out D and put in 600. So I kept the negative 0.08, I just took out the D, put in 600, I kept plus 50. Throw that into your calc exactly the way you see it. We need some units. 2 what? 2 liters. What does that tell you about your car? You are about to run out of gas because 2 liters is teeny tiny little amount of gas. So let's just use some logic here. 600 kilometers, are you driving in the city or outside the city? Well, you're probably outside the city unless you're circling the city a whole bunch of times. And so people are like, well, why would I need to know this? I have a gauge. It tells me when I'm getting empty. So why would mathematically you need to know when you're about to run out of gas? Well, if you're outside the city, and let's say you're going west, you're into Saskatchewan, how far apart are the gas stations? Pretty far. So it's not like in a city where you can drive a couple blocks and find a new one. So do you want to know when you're about to run out of gas? Yeah, because you can't fill up after the fact. You need to fill up before the fact. So it's great you have a gas gauge, but you still need to know what's happening with your gas. Has any of your parents ever run out of gas? It happens to everybody at some point. I've never run out, but I've like coasted in it like nothing. I have a 60-liter tank and I've put in 59.8 liters, which means there was like nothing left. Happens to everyone. Determine D when VD equals 26. Well, let's first talk about what does this mean. This is telling you you don't have a distance because they have the variable distance. It's telling you you have a volume. So what is this asking you in words? Find the distance you've driven or traveled when there is 26 liters left in the tank. Write that down however that makes sense to your head, in your head. It's asking you, how far have you driven? How far have you traveled? How far is the car gone? When there's 26 liters of gas left. How many of you have your beginners or have your real full driver's license? So you need to be aware of gas. And I understand as a woman that we don't care. I care my car is blue and it's pretty. That's really all I care about. Boys, you get how cars work. But let me tell you, the first time you run out of gas, you can call mom and dad and you can cry and they'll come save you. Maybe the second time. The third time, you're going to be on your own for this. Roughly, an SUV, a larger car, maybe a smaller truck, how big is the tank? See, you guys need to know this stuff because you need to know how much you have left. It's about 60 liters. 60 liters, I have an SUV, it's 60 liters. That's a small truck, a bigger car, an SUV. A normal sized car, so kind of a smaller car, not a truck. I just dropped my pen. Roughly how big is the tank? Bigger than 30? 40. So smaller car is 40, mid-sized car, SUV is 60. What about a big old truck? They're usually about 100, sometimes 80 if they're smaller trucks. So if you are driving your parents' car and it's a smaller car, you're looking at a 40-liter tank. If it's a bigger car, you're looking at about a 60. If you're driving a big truck, it's about 100. Well, that matters because 26, if you're driving a 40-liter tank, how much gas do you have left? Over half a tank, right? Because half of a 40-liter tank would be 20. So can you get to 7-Eleven and back? Sure. Could you cross Winnipeg and back? Yeah, Winnipeg's not that big. What if you're driving a 100-liter tank? How much gas do you have left? 100-liter tank, you got 26. A quarter. That's when it starts to go, Could you get across city and back? I don't know. That's where it gets a little sketchy. What if you're driving an SUV and you have a 60-liter tank? How much gas do you have left? About a third. A third's not bad. Really, especially, I'm now giving you a total gas lecture. In Winnipeg in winter, you don't want to go below a quarter of a tank because what happens when there's a lesser amount, it can freeze faster. So you don't want to go under a quarter in Winnipeg. So if you're like looking at the gas, you're like, oh my God, a quarter, you need to really fill up. Listen, girls, I understand cars are boring. I totally get that too, but there's a few things you need to know. You need to know how to change a tire, you need to know when you need to change your oil, and you need to know when you're running out of gas. Because at some point, there's not going to be a boy around to help you to do those things. So learn those things. There's my lecture for the day. How do we solve this? What do we do? What does this mean? Well, this is saying take the equation, which is negative 0.08D plus 50, and we know it's equal to 26. This now becomes a regular old equation from grade 8 and grade 9. How do we solve a linear equation? How do I get rid of plus 50? Subtract 50. What do I have on the left? What's still remaining? And on the right, I have my minus 50. Negative 14, negative 24 I just heard. You can use your calc for this if you need to. It'll be negative 24. How do I get rid of a coefficient? So even though it's negative, I'm not subtracting this, I'm multiplying. So how do I get rid of a coefficient? What's the opposite of multiplying? Dividing. So I'm going to divide each side by negative 0.08. Well, it can't be negative because we get a negative divided by a negative, so we know it's going to be positive. Plus, we can't drive a negative distance. And we need some kind of units, 300 what? Kilometers. So girls, here's my other tip. How far is 300 kilometers? Okay, so roughly if you're on the highway, how fast does a car go? What's highway driving speed? 100 kilometers. So what I do is I divide that by 100. How long did you drive, or in time? That's about 3 hours. Brandon's about 2, so you drove past Brandon. There's my little lecture for the day. How are we feeling?